Hi there. In this video, I want to talk about the Proximal Policy Optimization Algorithm. And this is one of the bases of reinforcement learning algorithm for policy optimization. From the name, you can guess, and published in 2017. And it is famous as PPO algorithm. You will see PPO in reinforcement learning paper a lot. It is introduced after TRPO, Trust Region Policy Optimization, and also after actor critique method. So if you are not familiar with those um, terms, maybe we will have covered them in the future videos, but in this video, we will talk about the proximal policy optimization. So if you don't know about the reinforcement learning, I will talk briefly about that. And finally, we will have an implementation. We will solve inverse pendulum. So basically, in proximal policy optimization, we are trying to optimize the policy. The previous method like using the deep Q learning or the vanilla, the policy gradient method, they have some limitation. So the limitation is that here is mentioned, like in Q learning, it failed on many simple problems and is poorly understood. Vanilla policy gradient method have poor data efficiency and robustness. And also the TRPO is relatively complicated and is not compatible with architecture that include noise such as dropout or parameter sharing between the policy and value function or with auxiliary tasks. So in reinforcement learning, we wanna optimize this formulation. What does that mean? So we are in one state, and in reinforcement learning, we are going to a next state. So I can say this is a state one, and this is a state two. When I'm going from a state one to a state two, I'm taking action. So the policy is rule that I can use in that environment or in that problem space to do an action. So if it is a deterministic, so I mean, if we know precisely that what action I should take, so it would be like if I am in the state one, I want a function or policy, show me what action I should take. So this is deterministic, but we know that the problem is not deterministic and the policy is like stochastic. So what I mean by that is, instead of having that, I will have something like, so we have that policy, stochastic policy, and we will say, if I am in that state, like state T, what is the best action I can take? So I can take like action T. So if I am in a state one, the best action is A1. Why it is best action? Because it is increasing my value. It has advantage over other actions. So it is like a correlation between the advantage function and stochastic policy function. So it means that by taking the action T in a state T, for example, I'm getting advantage negative. So it means that it is not a good action because the advantage is negative, and what we want to learn is that what is the best policy. So we want to optimize this policy. Somehow, if we were in a state ST and take an action AT, we will get the best value. In the inverse pendulum problem, for example, I have a base and I have inverse pendulum, and I am in that state. Maybe I am in this state, and the pendulum is falling down. So what is the best action? Policy optimization should give us something like this, that go right. So it should give us the best action to increase the value. The paper here explained that problem in another way. So it said, okay, we want to take an action from that optimization policy, but the problem is if I'm in that position and I'm suddenly say go right, and that action is not smooth, like instead of saying 1 centimeter, I just say 20 centimeter go right. So maybe that's make the pendulum in a bad situation, like like this way. There are some conditions that can be applied here. So we can say, for example, we want to maximize this, but the distance between the current policy and the next policy, the old policy and the next policy shouldn't be that much. We know that this type of optimization problem can be solved by the Lagrangian algorithm, and it means that we add a penalty like here, so we can bring that constraint into the main optimization problem, and we will have something like this. If we suppose that this term is like a ratio of the policy that we have, so they also said that this clip function can be used instead of this maximization here. So they define another formulation as clip. This clip is a lower bound on the LCPI, and LCPI is this one. This is a lower bound of that with a penalty for having too large of a policy update. Also, there is an adaptive KL penalty. So it means that we have that beta, but each time we know that we want to reach to a target. So each time, based on how much we are close to the target, we update the beta parameter. So if we are far from 90 degrees, we want to move faster. If we are very close, we want to move gentle to not suddenly go out of the scope of the stable point. Finally, they are providing this formulation, which is combination of the clip, MSE, square error loss of the values, and also the entropy of the policy. So they have different types of optimization policy defined, and they compare it with several other methods in the literature. And so the PPO is this one. So you can see that for maximization, we are getting a better performance. They also showed that this method can be used for any continuous problem. That's it. Let's go to implement some code. We want to focus on the inverse pendulum problem. Okay, let's jump to the Visual Studio Code for writing some code for PPO. I can call it main.ipynb, and okay, so I first load some of the libraries. I'm using the gem for the environments. So we need the matplotlib for showing the plot, the torch, and the optim for optimization functions, and the pandas. So we can create an agent, and we can create an agent config and put all of the variable of the agent config in that. And I will explain each of them during the implementation. We start with the init function of the agent. For that, we need to create a gem, create an environment, the card pool. And there are two types of action. If we say environment, the action space, and get the number of the actions, for card pool, we have two. It can go right or it can go left. So these two actions that we can take. We can have a training card pool. So if we are in the training stage, we need to train an MLP system. And for that, we need the optimizer. And for gradient, we can use the scheduler in order to control the learning rate. So at first, the loss is 0, and criterion, we will use the MSE loss. And also we need a memory, because we have an environment and we want to save some of the environment. We want to interact with the environment and save, like with this state, if we do this action, what reward we will get, and what would be the next step, and what is the action probability, and if it is terminated with that state and action, and how many iteration that we have done so far, and also the advantage function and the target that we are looking for. So this is for initialization. Let's jump to another part. We can create a new random game just by resetting the environment, sampling from the action, like it is just random, we can say right or left, and apply that action to the environment and get the new observation or new state, get the reward, and say, is it done or not? And info is just some information that we don't care now. The next thing that we can do is training the system. So we can write the training function. So we are in the first episode, and we will check that until the problem is not solved, we do the while loop. And every time we increase episode, and we start episode from 0, and we create a new game. So we have a game, we want to play it until its end. So we start the game again, and we play it until we can finish it again. So we do it repeatedly, maybe 100 times. So we have a good data in the memory, and we can then, using that data, train an agent. So when we get the state, we can say the current state is the state that we got from the environment, and we can say total episode reward so far is 1. So now we want to go to the main loop of the game, I mean the environment, and call it game because we can suppose it like a game. For each time we increase a step, and we increase the episode length, and we need a policy network we haven't created yet, but the policy network is trained by the PPO, and we get the probability what action we need to take. So it's like the pi function that we had in the paper. And if you are working with GPU, so it's good to have defined device somewhere like maybe here. We get the probability. This is logits of the network. And what we need to do is using the categorical random distribution, we just sample from. So maybe the action, the actor model or the pi model recommend us that you can go right with this probability, and you can go left with that probability. Maybe the probability of going right is higher, but we still give chance for going left to have most of the data distribution covered. So we want to create a categorical distribution from the probability that we had from the pi network, and we sample from it. So with high probability, it will choose the predicted correct action, but there is a chance that it's not. It's like a roulette wheel. So we get the action. Now it's time to act. So we have an action, and we need to apply that action to the environment. So we get the state, the reward, and terminal again, but this time we call it new state. We just want to be sure that if it is terminated, we just set the reward to -1. We want to update the memory. So we have the current state, we have the new state, we have a reward. Of course, we can normalize it. And we have the action, is it terminated? We have the probability, and probability of the action that we selected is important for us. So we have all these, and we save it in the memory. After doing that, now it's time to set the current state, and we can increase the total episode reward. So if terminal is true, so we can get the episode length so far. Total episode reward can be go to the reward history that we had in training. So for this trajectory, we can say for this trajectory, we will save the reward history, and we have the average reward also. We also have finish pass. So we will write this function. This function is used after we know that everything is done. We need to do something with the memory, and we prepare everything for the training. So, and we say if the reward history is bigger than 100, this is something that we can work on. And we can say solve this true. So we are saying that if we have 100 times iterations, and also the rewards that we got from the trajectories is satisfying this condition, so we can say the problem is solved. After that, we have print the trajectory that currently we have, and also reset the environment and break from this while loop and go to the next episode again. We can create a like update frequency, and for every time that we get some information, we can update the network. It's good to close the environment because we don't need the environment anymore after the final while loop is finished. This is the place that we apply the PPO algorithm here. So I can say this is the PPO, and we are updating the pi network here The pi network, as I said, we use it here, the policy network. And policy network, as I said here, is defined by this MLP policy, and we will create that network. And now it's time just to update that network. So we need to train it. We need to apply the state that we have currently in the memory to the policy network that we have, and we can say these are the pi that we have. These are the actions that we can have. We want to have these pi, but based on the action. Like if you want a first one, if you want a first index, you want a second index. So just pick those action, and each pi row is 2 column based on the number of action that we had. And the action set, for example, select action 0. So from the pi, it will select the first column of that row. So the gather function is doing that for us. You can get the old probability because we currently save the action probability in the memory. You remember this one, but this one is selected by the action that we had from the categorical distribution. And this time is applied the current state again on the system and get the new probability. So we have the new probability and old probability. The reason that we are doing that, because if you see the paper again, there was some ratio that we need to be sure that the new probability and old probability shouldn't be much far from each other. So if you remember that we had a ratio, and it is okay that apply exponential to them, because in that case, we can just use the negative to create that ratio. So we have new probability divided by the old probability. We had the surrogate loss. Surrogate loss is based on the paper. So we had the clamp, multiply it by the advantage. We have that function here as a surrogate 1, as surrogate 2. So if you remember, we had like C1 multiplied by first surrogate, C2 by second surrogate, and stuff like that. So we have a complete loss here. This is the PPO. Remember that formulation in the paper. So we have finally the average of the 3 different losses. The first loss, the minimum between surrogate 1 and 2. The second one, which is this one, the Haber loss. Yeah, the final is the entropy loss. Those coefficients are defined here. So we can change them based on what we need. So after creating the loss, the only thing that we need to do is, using the optimizer that we have created, we make it 0, apply the loss back to the network. We haven't created network yet, and we apply the optimizer 1 step and a scheduler 1 step. That's it. As I said, we had add memory here, but we haven't created that add memory yet. So maybe here I can create that add memory function. So what is it's doing? It's just adding data to the memory, and if number of count is passed from the memory size, we can remove from the first part of the memory. Like we have 128 capacity in the memory. So if the number 129 comes, the first will go. So this is just like a FIFO with limited size. So we will append all of the information to the memory. So we have another function called finish path, and we call that finish path here after we know that we are done. We have created different steps, we save them in the memory until we are done. So we are done and we need to finish that pass. And we know in what episode we are done. So what we need to do now, we need to calculate the advantage function. We know the length of the pass. So each time we are adding different information to the memory. So this is like a continuous memory, but we need to get from lengths from like if the number of episodes that we had is like 10, so we need to get the 10 recent samples because these are related to the current episode. So we get the state reward, the state, new state, is it done or not, and now we can define the TD target, the target that we are looking into. So we have the policy network, and from the policy network, we can get the value. So we can say, in this policy network, what is the value? And we apply the state, and it gives us some value. But we know that for calculating the target, we need to add the reward plus a gamma to the gamma multiplied by value multiplied by is it done or not. So what we can do for calculating the advantage is we can create a delta function for each state. What is the target level and what is the value that we got, and we have their difference. So this is our delta function. And for each delta function, we can use the multiplying the gamma, the lambda, and the advantage function. The gamma and lambda is defined also in the config agent. So we have gamma and also the lambda. Finally, we can save the target and also the advantage into the memory. So what else is remained is creating the MLP policy. So I want to create it before creating the agent. So the MLP policy is like any deep learning network, but we have two sort of network. One for pi, which get the action, we get the state and return the action. And one is the value that we get the state and say what is the value of that. So we use that V for calculating the advantage function here. So for running the program, we need to create an agent, and we can say just train it. Another thing that we can do is for showing the performance of the reward that we train the network, we can maybe plot the graph after a specific time. So let's have this plot graph somewhere before creating an agent. Maybe after here, we can say if episode is 0, so we can plot. We can plot the reward history and the average reward. These are one of the reasons that we put them there. So we need an agent and we need to train it. Let's see, is there any problem? So plot every is not defined. Sorry, I should say, I think self dot plot every, that makes sense. So let's train the system. So I can see the losses. Okay, it's trained, and now you can see we are in a very good position. We can use this for rendering an episode and save it as a GIF. I'm getting the code from the TensorFlow page. So let me share my folders to see the saved GIF file. Yeah, you can see that it's going right, it's going left, so it's simulating. And I will share the original page of the code that I got from. I tried to understand it well and then implemented it in Jupyter Notebook. It was not in the Jupyter, it was just in the class-based, and I just put it here. So thank you for your time and attention. Please leave comments, subscribe, and share with your friends. Have fun.